Hello, everyone, and welcome to week 13 of Qubit by Qubit's Intro to Quantum Computing. We are back here after this past week's lecture on Sunday to finish off our trilogy on quantum mechanics. So for the past 2 weeks, we have had quantum mechanics 1, quantum mechanics 2. Now we're on quantum mechanics 3, which will round out sort of all of the physics and mathematical theory behind quantum mechanics before we move into sort of the final stage of the course on quantum computing programming. So, good news if the last couple of weeks have not really been your thing, that's totally okay. It's been certainly more physics focused. And, if you did enjoy it, hopefully you also enjoy this lab. We're gonna pull some loose strings together to hopefully make sure that everything makes sense in context. And then, yeah, like I said, next week we're gonna go into, well, I think next week is a little bit more quantum computing specific math. And then following that, probably I won't be writing on my tablet very much. We will just be coding for the rest of the course. So that's a bit of a preview of what's coming up. But for right now, we are looking more at the physics of quantum mechanics. So a quick program for today, pretty standard. We'll start off with the Canvas attendance quiz. We'll launch into our pre-lab Zoom feedback. We do have one question that we're going to address from last week that we saw come up more frequently. Then we'll get into the core of the lab content, followed by post-lab Zoom feedback as well. Okay, so the Canvas attendance quiz. Go ahead, open up your browser. We are lab number 1 with the quiz password this week, 6039. So that should get you into the quiz. There should be 2 questions there that you see. The first one is, on a scale of 1 to 5, how much do you agree or disagree with the following statement? I'm glad we took the time to learn the math concepts inherent to quantum computing. So technically speaking, we could have just taught you, linear algebra, right? So vectors and matrices, and that's kind of all you need to understand quantum programming with Qiskit, for example, that we'll start doing a bit later on. But we have tried to teach you more of the sort of physics and mathematical background so that some of this makes a little bit more sense. And so that's kind of what this question is asking. How glad are you that we took the time to learn that extra math? Or would you rather have just jumped right into the programming without too much background and only with what's strictly required? Then the second question is just, in general, do you like math? I guess we're just gathering this for our own interest. I think you can probably tell that most of us enjoy math. We're just kind of curious where the rest of our audience is at on that. I will open up the chat here if anybody has issues with Canvas or filling out this quiz. As always, please make sure you do fill it out. It does count for your lab attendance. So there's no correct answer, but you should fill out the quiz. You're getting 0 out of 0. Okay. Is anybody else? Is that different from what you usually see? I apologize. I'm not sure what you usually see. Okay, so everyone's getting it. Oh, you usually get scored out of 1. Okay. Okay, I mean, if everybody's getting that, I wouldn't worry about it, but I will definitely make note of that to our admin staff, just to make sure that everything gets counted correctly. Thanks for telling me. Okay, awesome. So let's go on to the pre-lab Zoom feedback. I will pop up a poll on your screen as usual. So let me know, oops, sorry, next slide, there we go. On a scale of 1 to 5, how would you rate your understanding of this week's content? So thinking back to the lecture on Sunday, how did you feel? 5 is like you understood everything, no problem. 1 is you really felt lost. So let me know how you're feeling. Okay, so this week seems to have been a bit more challenging. That's good to know for sure. So if anybody felt a little bit less comfortable with some of this week's material, could you let me know what that is exactly in the chat? Like, was it the postulates? Was it more on sort of, well, yeah, I guess, was it the postulates? Is that the main confusing piece here? Postulates, okay. Lab password is 6039, which is just, oops, which is just in the bottom right there. Postulates, postulates, postulates. Okay, good to know. Thank you. We'll definitely spend some time on postulates today, for sure. Okay, so before we go into this lab's content though, let's do a quick question from last week. We had a few people ask, what happens if we try and measure spin along the X and Z axes at the same time? So just a quick clarification before I answer this. This is not measuring Z then X, right? So some of the questions that were in your homework had these weird setups where like you would measure in the Z axis first, and then you would measure in the X axis. That's not what we're talking about here. What we're talking about here is, number one, I guess, could you in theory measure spin along X and Z at the same time? And B, if you can, what happens in that case? So I'm going to bring back the picture of the Stern-Gerlach machine that we had last week. So just a quick reminder, we had our Stern-Gerlach magnets. Magnetic field lines go from north to south like this. Our electron can be thought of as a little bar magnet, north-south like that. And then we send our electron through and we expect it to either deflect up toward the top or down toward the bottom. Okay, so what would it even look like to try and measure along Z and X? So as a reminder, the reason we call this measuring along Z is because the magnetic field lines point in the vertical or Z direction. So if I look at this from the side, so suppose my eye is over here, right? I'm looking from the side of it, I would see something like this: the south on the top and the north on the bottom, right? And then our magnetic field lines go from bottom to top. And our electron is, somewhere in here. Now, we could pretty easily just put another set of magnets here, right? We could put a south magnet there, a north magnet here. And then we have magnetic field lines running in both the Z direction and in the X direction. And so this is kind of, in my mind, the closest you could get to measuring both at the same time. The question then is, where is this electron going to deflect, right? When we had just the Z axis, it went either up or down. If we had just the X axis, it would go left or right. So what do we have now? What do you think will happen here? So the easiest way I think to think about this is to go back to fundamentals, right? What are we really talking about here? We're talking about magnets. Your electron is a little bar magnet, and there's magnetic field lines inside here, generated by the Z and the X directions. So you could think of this in two ways. One would be sort of as a superposition of Z and X, and that's a totally valid way of thinking about it. But the other way to think about it would just be as combined magnetic field lines, right? So if you have two south magnets up here, the general direction of your magnetic field lines will be like this, right? From the side with lots of north magnets to the side with lots of south magnets. And if you remember from last week, one of the things we said about the Stern-Gerlach experiment is that it will measure only in the direction of the magnetic field or exactly in the opposite direction. There's only two possibilities. And so indeed, if you sent an electron through this, it would either deflect to the top left or down to the bottom right. And those would be the two possible measurement states. So we would have like a spin top left and a spin bottom right as our two basis states. So don't worry too much about that. Like this, isn't really used. I don't think I've ever seen a diagram like this, but it's a point of curiosity. And if you had this question, hopefully that helps. Okay, yeah, so to people who are DMing me about their score on the quiz being 0 out of 0, everybody else seems to have gotten the same thing. I'm not sure what's wrong, but I will definitely bring it up with the course staff and you'll all be fine, right? They're definitely not gonna take marks off of every single person. So if electron is, I'll just answer this question now because Stern-Gerlach is gonna come back in a few slides, so it's important. If the electron is spin up and down, right, why does it respond to the X direction field? So that's not exactly this question here. So just to be clear for everyone, this is a separate question now. And the student is asking, why does an electron with a spin in the z direction, for example, here, why does it sort of respond in the x direction when it goes through two magnets? Well, I mean, one answer could just be that this is what's observed, right? So it's a little bit hard to draw, but you can imagine having, the south magnet kind of, oops, I should draw it like a bar. South magnet over here, and then the north magnet kind of here, right? And then you're sending a spin up electron through those two magnets. We will talk about why in this lab exactly why you only get the spin right or spin left results. So the way to think about this from last week is to think about the electron, instead of being spin up, you think about it as a superposition of spin right and spin left. And that'll tell you that there's a 50% chance it ends up deflecting to the left and a 50% chance it ends up deflecting to the right. Why that is a great question, and we will get to it shortly. And yes, this is correct. So the situation where you have an x direction magnetic field and a z direction spin, they're not orthogonal, right? So the spin up direction is a combination of the two x directions. Okay, so let's move on here. Quick overview of what we're doing today. So as I said before, the beginning part of today is basically tying a few things together, right? Filling in the last piece of the puzzle on this whole quantum mechanics, wave particle duality, superposition, like why all of this matters for quantum computing, all that kind of stuff we've talked about in pieces over the past 2 weeks, but now we're going to bring it all together. And how that is going to happen is basically by explaining why quantum computing and quantum mechanics is called quantum in the first place. What is quantization? Why does it happen? And how does it affect the mathematics? So that'll be the first part. The second part, though, which I'll try and spend more time on, is the postulates of quantum mechanics. And basically the way we'll do this, we'll have a very quick review of the postulates that you went over in the lecture. But then we're going to walk through the Stern-Gerlach experiment again, but using the postulates, right? So we'll try and predict what happens in the Stern-Gerlach experiment using the postulates of quantum mechanics so that you have a concrete example of how to apply them in an actual problem. And then the optional content today is a little bit more on guitar strings. We're going to talk about guitar strings, in the regular part of the lab too. But yeah, this optional content is a bit on something called Fourier analysis, which sounds scary, but I promise is actually just a very beautiful visualization. And it helps explain how superposition arises from a complicated world. I'll just leave it at that for now, but it's a cool little section. It will take me a bit longer. So I'll do it at the end as usual, but yeah, stick around if that sounds interesting. Okay, so let's go back to a slide that we have seen before. This is the motivation for why we're studying quantum mechanics for quantum computing. And I introduced it with these 3 statements. The first one, qubits are made of objects that show wave and particle-like behavior. This one doesn't really require any further explanation. It's kind of just, we can take it as a fact that humans came up with a name for stuff that is both wave and particle-like, and we call it qubits, right? So it's kind of just a definition. Okay, what about the second point though? The second point is the one that we're going to focus on here. Quantum mechanics is the mathematical description of objects that show such behavior. And the key question we're going to ask is, why is this the case, right? So when we think about the mathematical description, so quantum mechanics, we think about things like superposition, right? The whole reason we introduced all these vectors and matrices and stuff was so that we could have superposition, right? That's sort of like the fundamental piece of quantum mechanics. But why does wave-particle duality, this wave and particle-like behavior that we talked about, why should that lead to superposition and quantum mechanics in the first place? Okay, so to do this, we're going to talk about musical instruments. So if you play a musical instrument here, here are a bunch from around the world. As I said, we're going to mainly focus on the idea of a guitar string. But this same argument works for airwaves inside of a wind instrument. It works for strings on a violin, strings on a guitar, of course. So if you play a musical instrument, hopefully some of this makes sense to you. Even if you don't, though, obviously, I'm going to explain everything. Okay, So how does any of this relate to musical instruments? Well, we'll start off just with a fun quote. I guess this doesn't really answer the question yet, but there's a quote from Einstein who said, "If I were not a physicist, I would probably be a musician. I often think in music. I cannot tell if I would have done anything creative or any creative work of importance in music, but I do know that I get most joy in life out of my violin." So if you play a musical instrument, great job. You are already on your way to becoming a world-renowned physicist. All right, so let's think a little bit about strings, right? So for example, here's a guitar string. Let's just picture that, right? Now I want you to imagine what happens if you pluck a guitar string, right? So essentially what you have the string fixed on one end, right? So over here, your string is tied down, and your string is also tied down up here. So I know the picture shows them with their fingers on the strings, but imagine you don't have your fingers on the string, you just pluck one of the strings. And the question is, what does it look like? So try and think about that for a second. Let me just see if there's anything in the chat. So somebody asks, why have we, sorry, I'm jumping back to Stern-Gerlach for a moment. I should have checked, but why have we taken the right and left spin for the superposition in the Stern-Gerlach experiment? That will also be explained by one of the postulates, so we will get to that. If I understand correctly, up and down are orthogonal, and so are left and right, but they are not orthogonal to each other. That is exactly correct, yes. So if you can write a state as a superposition of two other states, the original state is not orthogonal to those other two, basically. Okay, if there's any quantum math specific to Stern-Gerlach, please share them. That's the second half of the lab. Are we talking about string theory? No, not really. I guess you could kind of think about this as like a super introduction to it. This is more supposed to be an analogy, though, to sort of think about quantum mechanics and why quantization arises from wave-particle duality. Okay. Okay, so yes, everybody's now saying what happens. Exactly. So let's go to the next slide and see how this string looks, right? So probably what you imagined, well, based on how I described it, is the first one here, right? You would imagine it staying fixed at both ends and vibrating up and down in this sort of wave-like pattern, right? Okay, we're going to call this the first mode. Now, how would I get the second mode? Well, if I just place my finger right in the middle here and just lightly press down on the string, it's still going to be fixed on the two ends, but now the string is kind of fixed in the middle as well, right? And what you end up with is two kind of sub-modes here. So on the left, we have a first mode, and on the right, we have a first mode, right? Each of those patterns is kind of just a miniature version of what we saw up top here. And we can extend this idea, of course, right? If I put my finger in two places, then we will get three copies of the first mode. And we call these things just numbered. Second mode because there's two copies, third mode because there's three copies, and so on and so on. So pretty straightforward naming, right? And the string will always vibrate in one of these specific shapes, and we're going to call them modes. That's pretty much it, just the definition, right? Now, if you look at this picture of a guitar, sorry, it's kind of cool. You can see some of the different modes of the string, right? So for example, this mode here looks to be very frequent, right? It's oscillating quite frequently. This one is probably a little bit less frequent. So maybe this one is the, I don't know, 40th mode, right? Because there's 40 copies of the first mode. Maybe this one is the 50th mode, right? So you can imagine that these things go up in number just based on how many little wiggles there are in a string at a time. Now, the question I want you to think about, though, is why this happens. Why are there only certain patterns that you can see on a string, right? I have just listed them out for you. I've said you will see the first mode, the second mode, the third mode. There are infinitely many, but there's also a bunch of patterns that you can't see, right? Or at least I'm claiming you cannot see. For example, you would not see something that looks like, I don't know, this. right? Just some other random shape that doesn't fit what we saw in the previous slide, I'm claiming that you cannot see that pattern on a string. So think about why that is. Why do our strings have to appear in these specific modes? So the answer to that is confinement. And this is the sort of fundamental principle of why quantum mechanics exists, really. So all these different modes, they're a result of confining the oscillation of the string between 2 points, right? So in all of our diagrams here, the common element is that they're fixed on their 2 sides. They are confined to this one little area in which they can vibrate. Now, these modes, by the way, just another piece of terminology, I guess. In a more mathematical sense, we would call them eigenfunctions. And if you recognize that word eigen, yes, that is absolutely related to eigenvectors, which we'll get to soon. Okay, so pretty pictures. This is all cool so far. Now let's go down to the quantum scale. Why do we care about these things? Well, at the small scale, everything, remember, can behave as a wave, right? I think the previous lab, we talked about how there's this wave particle duality thing, which basically says small scale objects have both wave and particle-like properties. So if everything at the small scale has wave-like properties, excuse me, then they can show this thing called quantization, right? So quantization, by the way, as a term, all that means is that you get distinct modes, right? It's pretty much the concept I was just talking about. Instead of having infinitely many, or sorry, instead of being able to see any vibrational pattern on the string, there's only certain patterns you can see. And we call that quantization, just because it's, the modes are divided into specific quanta, which are just separate discrete categories. So then the way that we will usually do this is, if you picture each of these strings as a quantum state, which let's do that for now, we can use just the top 2 modes, for example, as qubit states, right? So maybe we call the first mode ket0 and the second mode ket1, and then we're just going to ignore everything else higher than that, right? And this is actually usually what happens. Usually we set the first 2 modes to be our qubits, and we ignore everything else. So to recap, the really important thing to take away from this slide, in my opinion, is sort of this linking between wave particle duality and quantization. So wave particle duality is something we saw in the double slit experiment, right? That showed us electrons propagate like waves. Now, assuming they behave like waves, we will see this same pattern of distinct modes whenever you confine the electron in some way, right? So here we've confined a string by tying it down on both ends. You can imagine there's other ways of confining an electron, which I'll talk about in a second. But if you confine an electron, the electron is a wave, and so the electron will only take on specific modes. That's the key takeaway here. So acting like a wave plus confinement equals quantization. I know that, by the way, like this was really hard for me to wrap my head around the first time I learned it. So please feel free to ask questions in chat. I don't know how good of a job I'm doing at explaining this. So somebody asks, the eigenfunction I'm talking about in the previous slide, is that the eigenfunction of the wave operator? Yes. So that would be, in this case, it would be like the eigenfunction of the, oh my gosh, I'm blanking on the word. Wave function. It would be the eigenfunction of the wave function. Right, so somebody says, so are electrons literally moving like the modes of a wave? Not really. I wouldn't try and picture this as a literal thing. The reason we're talking about guitar strings and all of this is to try and explain why wave behavior leads to quantization. And it's basically about this notion of confinement. If you confine something that behaves like a wave, it will only take these certain discrete forms. What does it mean to confine? I'll get to that on the next slide, so hold that question. Are each crest and trough a quantization state or mode? So the different states here are just the multiple modes of vibration, right? So if my string is vibrating like this, it's in the first mode. If my string is vibrating like this, it's in the second mode, and so on. So it's not really related to the crests and, I mean, I guess you could count the number of crests and troughs, and that would tell you the mode. Yes, yeah, so this is a great point. Confinement is also called a boundary condition, totally true. And a lot of systems have these boundary conditions. So actually, let me get on to the next slide where we'll talk about what confinement usually looks like. And it has to do with electron orbitals. Okay, so now let's think about some actual physical objects, right? The guitar string thing is basically an analogy, but I promise this holds up in the nano world as well. Here are a bunch of examples of qubits, right? We can use all of these things in some ways as a qubit for a quantum computer. And there's a bunch of different challenges of using these qubits. So let me explain a little bit. First of all, let's talk about atomic orbitals, right? So electrons are something that behave like waves. The confusing part here, and what makes it difficult to visualize electrons and atomic orbitals and stuff, is that a guitar string being confined at two ends is one-dimensional, right? Unfortunately, electrons exist not in 1 or 2 dimensions, but in 3 dimensions. So electrons are these 3-dimensional waves that have 3-dimensional confinements. They still experience the same effect where they get trapped into these certain modes, but it's much more difficult to visualize, right? Because we're not really used to thinking about waves and confinement in 3 dimensions. Now, to the earlier point about what confinement means in this case, it's exactly the same as asking, why do electrons stay inside an atom, right? So in the electron and atom case, the confinement is just the Coulomb force holding them in. So it's not literally somebody pinching the two ends of a string. There's nothing literally pinching the two ends of an electron, but there is this kind of like 3D envelope of the Coulomb force that confines it inside the atom and creates these specific modes, like we saw with the guitar string. So it's a bit of a leap, I know, to go from 1 dimensions to 3 dimensions. But again, the fundamental idea here is just that waves being confined, in other words, electrons being held by the Coulomb force, waves being confined will show these quantized modes of vibration. Okay, so another example then of a particular qubit would be trapped ions. So again, these can behave in wave and particle-like manners. The difference here is that with trapped ions, humans are actually applying some external force to trap the ions in place. And so in this case, the force that holds the ion in one stationary location, that is the confinement, right? And so a lot of times in this case, we use something called optical tweezers, which we're not going to get into, but the optical tweezers exert a force that holds the atom, suspends it in midair. And the forces that are holding it in midair are the confinement. And that confinement causes the atom to take only specific modes. Okay. So that's pretty much all I wanted to talk about, linking quantization to waves. Any more questions on this? I will say, I took a brief look at the homework for this week. There's nothing on this topic specifically. I think it would be quite difficult to ask you questions based on these things. I think this entire section of the lab, though, is really trying to give you a more intuitive understanding for why all of these different concepts we've learned, from wave-particle duality to superposition, and like quantum states, and why the Stern-Gerlach machine only measures in one direction or the other, how all of those things connect. And sort of like the missing puzzle piece here was this confinement idea. So one person asks, why are modes important? So modes are important because those are the only physical states that a qubit can be in. So it's kind of the same as me saying, if we're talking about position, suppose we're considering position, and my pen exhibited wave-like behavior, we're saying that my pen could only be in distinct locations, right? There are some locations where my pen cannot exist, right? Just like there are some shapes of the string that cannot exist because of the confinement. And so that is what gives rise to these discrete states, ket 0 and ket 1. And that's why we describe things as superpositions. Okay, so what are the mode equivalents for electrons? Is it spin, position? So this is a great question. Pretty much, so every physical property of a subatomic particle, so for example, an electron, has these different modes. So there are modes of position, there's modes of spin, there's modes of momentum, there's modes of charge, like all of these different things behave in this manner where you have confinement and you have specific modes arising from that confinement. So we'll talk about this actually when we get to postulates, but whenever you are doing a quantum mechanics problem, you'll usually be told what that physical property is. So you'll be told, okay, we're considering position here, and then carry on with the problem. But these same effects, I mean, it looks slightly different for different physical properties, obviously, but these same effects arise in any physical property of a quantum object. Okay, so there's a lot of questions. I think I'm going to try and move on just to, oh, sure, I will explain trapped ions once again. A few people asked that. So trapped ion is a type of quantum computer, which I won't go too much more into, but the basic idea is that you have ions, which are just an atom with one electron stripped away, and you trap these ions in typically a linear fashion like this. So here, what you're looking at, I guess I should have explained that. What you're actually looking at here is individual atoms being trapped in a line. So each of these colorful blobs is an atom. And then what you do is you use the various states of these atoms to do a quantum computation, right? So literally, the first atom will be a qubit, the second atom will be a qubit, third atom will be a qubit. So like this machine here is a 6-qubit device. The way that you hold those atoms in those positions is a fascinating subject. You can look up optical tweezers to understand a little bit how that works. But yeah, there are ways to literally hold an electron stationary in midair using lasers, which I think is awesome. Okay, so I am going to move on just for the sake of time, but I, once again, totally encourage you, if you have more questions, please go ahead and ask them on Piazza. Okay, so let's go to the postulates of quantum mechanics. Like I said, we're going to start off with a quick review of what they are, and I am going to go kind of fast through this because we're going to get on to sort of an extended example throughout the rest of the lab that hopefully helps solidify these concepts. Okay, first postulate, a quantum state is represented by its wave function, ket psi. Cool, this is called, we're going to call this the wave function postulate. Second one is that classical observables become operators in quantum mechanics. We call this the operators postulate. Now, I will pause here briefly just to explain some of these words because I know they can be confusing. An observable is literally just anything you can measure. Okay, so complicated word, yes, but a very simple concept. Anything you can measure. So examples of observables would be position, momentum, spin, charge, number of electrons, like any of those things can be observables. Now, what this postulate is telling us is that anything you can measure in the world of quantum mechanics becomes an operator. What is an operator? An operator is just a matrix. So lots of new terms here, but the basic idea is anything you measure becomes a matrix in quantum mechanics. Cool, that's the operators postulate. Next, the only possible results of measuring an observable, so again, measuring a thing that you can measure, that's all that means, taking a measurement. The only possible results of a measurement are the eigenvalues of its operator. This is called the observation postulate. So again, just to break this down, you measure something. So this is the same, you can literally picture like taking a tape measure and measuring the length of your desk, right? That's measuring something. But in the quantum world, when you measure, right, if you measure with a tape measure, there's infinitely many different measurements you could take, right? You could measure something to be 8.5 centimeters or 8.56 centimeters or 8.59876 centimeters. Like there's infinite precision in what you could measure. But in quantum mechanics, remember, there's only distinct modes. There's some things that you just won't see. And so the things you can see are the eigenvalues of the matrix linked to that observable. Okay. Next up, the probability of observing an eigenvalue is the modulus square of the inner product of the corresponding eigenvector with psi, which is a mouthful called the probability postulate. But this we already talked about in a previous lab. We had something along the lines of like, oh, the probability of being in the zero state was equal to the inner product of the zero state with ket psi all squared, right? And this postulate is literally just that equation written down in words. Next up, after measurement, psi is equal to the eigenvector corresponding to the observed eigenvalue, the collapse postulate. So all this is saying is that after you take a measurement, again, this is something that does not make sense in our world, but in the quantum world, taking a measurement changes the state. Remember, we talked a lot about this last week. Taking the measure, like measuring a property of a quantum object changes the quantum object itself. How does it change, you might ask? That's what this postulate says. It changes to the eigenvector corresponding to the measurement you took. Okay, and then last one, if you have a state psi and you're evolving in time, which just means you're letting that state change over time, the way you represent that mathematically is by applying an operator. So again, applying an operator is just more jargon for multiplying by a matrix. So one of the things that can be really scary reading these postulates of quantum mechanics is that they do use a lot of quantum specific terminology, right? So things like operators, observables, and well, I guess those are kind of and like applying an operator. All of these terms just map directly to things you're familiar with, I promise. It's just you have to get used to the jargon that's used in quantum mechanics, which does take a while. And this last one is called the evolution postulate. Okay, so I'm going to hold off on the questions now because I want to go through an example first in hopes that the example answers a bunch of your questions. But I promise I will pause for more questions on these postulates toward the end. Okay, so let's return to the Stern-Gerlach experiment. This is the exact same slide we saw last week. So again, just to do a quick review, we have our magnets, we have our electron, which you can think of as a little bar magnet, north-south like that. And we're going to fire our electron through these magnets, and it's going to deflect either up or down. That's basically what we talked about last week. And this whole process is effectively a way of measuring spin, right? If the electron was spin up, it would light up the screen here. And so we would have measured it as spin up. And if the electron hit the screen down here, then it had to have been spin down. And so we measure it as spin down. Now recall that when you measure from the Stern-Gerlach experiment, the spin always has only two directions, either in the direction of the magnetic field lines or exactly opposite to it. And so again, that's the spin up and spin down measurements we can take. So I'll be the first to admit that this whole setup is a way more convoluted way of measuring something than just a tape measure on your desk, right? But it is the same concept. You want to find out some physical property of the electron. And so this is one way to figure out whether it's spin up or spin down. And that's all we're doing in the Stern-Gerlach experiment. Okay, so let's tackle the first, well, it's not the first in order, but let's tackle one of the postulates, that classical observables become operators in quantum mechanics. Again, that's called the operators postulate. So how does this apply to the Stern-Gerlach experiment? Well, in the Stern-Gerlach experiment, the observable, which again, just the thing that we're measuring, is spin. The whole experiment is there to try and measure spin. Now, we can measure spin along different directions, right? We can measure it in the z-axis, in the x-axis, I guess kind of in the y-axis, although we didn't really talk about that. And so for each of those possible measurements, right, you can measure it along the z-axis, measure it along the x-axis. Each of those has an associated observable. Or sorry, an associated operator. See, even I'm getting confused with the terms here. So observable, thing you measure, right? So if you measure spin in the z-axis, this postulate tells us that there is a matrix or operator associated with that measurement. And in this case, we know that that's the Z matrix, right? And we can just write out what we know the definition of the Z matrix is. Now, you can do the same thing with all of the other directions. You can, instead of measuring in the Z direction, you can measure in X or Y, and the associated operator or matrix just changes for that, right? So the operator would become X or Y. So that's how this first postulate actually works in a real example. Whatever you're measuring, right, in the world of quantum mechanics becomes a matrix. And in this case, it's just going to be the Z or sigma Z, X sigma X, Y sigma Y. Okay, let's try another postulate and see how it works. This is the observation postulate, and it says the only possible results of measuring an observable, so again, just measuring something you can measure, which is redundant, but the only possible results of taking a measurement are the eigenvalues of its operator. Okay, so the previous postulate told us what the operators are, right? They were these Z, X, and Y matrices. Those are our operators. This one is now telling us to consider the eigenvalues of those operators. Okay, so we learned about eigenvalues and eigenvectors last semester. If you need a review on that, you can definitely go back and watch one of those lectures. But I'll just throw down the answers here. Those are the eigenvalues and eigenvectors for these three operators. Okay, so the eigenvalues are in green, the eigenvectors are in blue. Just as a quick reminder of what it means to have eigenvalues and eigenvectors and stuff, it means this. If you multiply the matrix by an eigenvector, then what you get is just an eigenvalue times that same eigenvector, right? So the key thing here is that when you compute this, you don't have a matrix on the other side anymore, right? The Z disappears, it becomes just a number. That number is your eigenvalue. But crucially, the state you have on both sides, the vectors, they match, right? And that they have to match to be called eigenvalues and eigenvectors. Okay, so sorry, returning then to this observation postulate, all it's saying is that, okay, stringing the two postulates together, if we measure in the Z direction, that is associated with an operator matrix, Z, and the only possible measurements that we can measure, so again, like I'm measuring the length of my desk, the only two quantities I can measure are the eigenvalues of that matrix. So in this case, the only two quantities I can measure for spin in the Z direction is 1 and -1. Okay, let's do another one. Oh, I'm sorry, there's a problem now. Okay, so suppose we're measuring in the Z direction, right? We're measuring along the Z axis. And so we know that we're dealing with this operator matrix. So first question, what are the possible outcomes? And I'll throw up a poll for this. Oops. So the first question is, what are the possible outcomes of measuring spin along the Z axis? So remember, think about the two postulates I just said. When you're measuring something, it's associated with an operator. Okay, we got that. That's the Z matrix. Then the second postulate said, when you look at the value or the quantity obtained from that measurement, it always has to be an eigenvalue of the operator. Okay, so think about that. Always has to be an eigenvalue. What do you think the answer here is? I'll wait until about 50% of you have answered, and then I will go ahead and solve it myself. Now, in the meantime, let me see if there's, it seems like everyone's been answering each other's questions, which is awesome to see. So one person asks, how does an operator work? Can we say there's an analogy of the math calculation to something that we see in our day-to-day world? Yes, actually, yes, there is. And that will be the bonus content. So or bonus optional content. The optional content at the end is going to describe how these postulates basically relate to a guitar string. And so again, the reason we keep coming back to this idea of a guitar string is that it's in one dimension. And so it's a lot easier to think about. The only difference, though, is that quantum objects exist in 3 dimensions. It's the same properties and the same ideas otherwise. Okay, so about 2/3 of you have answered. So I'm going to go ahead and work on this myself. Now, again, the question here is, what are the possible outcomes of measuring spin along the z-axis? So if I relate this back to measuring my desk, I take my measuring tape, put it across my desk, and I look at how long my desk is. And maybe I get it's 120 centimeters long, right? Now, of course, in the real world, we know that desks can be any length you want, right? They can be 120, they could be 121, they could be 120.5, 120.25. It doesn't matter, right? There's infinitely many lengths that a desk could be. But in quantum mechanics, it's different because of that postulate that says the only possible outcomes are the eigenvalues of your operator. So what you would actually do in a problem like this, you first identify your operator. So I've done that. We're measuring in the z-axis. That means we're dealing with this matrix. This step should be pretty easy because the problem will describe in plain English what you're measuring. And then you basically just have to go to one of our slides or one of the resources you have and look up what the matrix representation of that measurement is, right? You'll always be given that. Step 2, then, is to figure out what the eigenvalues of this matrix are. So I'm not going to work through that problem here just for the sake of time. But if you need a refresher, our linear algebra labs covered how to compute eigenvalues and eigenvectors. So I've done that here. We just compute the eigenvalues and eigenvectors of this Z matrix. And the postulate tells us the possible outcomes are the eigenvalues. So the correct answers here are 1 and -1. Now, the answers in the Zoom poll were purposefully misleading and confusing. So I think the number one thing to remember here with these postulate questions, you really have to read the postulates carefully, right? And this is where I think a lot of people get tripped up. There's a lot of very similar concepts floating around, right? There's matrices, there's the eigenvalues and eigenvectors of those matrices, there's measurements, values of measurements, state collapse, like all of these things are connected. And so a lot of them can be confusing to actually disambiguate. But I think my number one, I guess, piece of advice for doing these kinds of questions is literally, for example, have this slide, where was it? Like have a slide with a summary of all the different postulates, have that open next to you, and just make sure you read them really carefully. So here, the biggest error that people made was saying that the outcomes of these measurements would be ket 0 or ket 1, right? So that's, as a reminder, that's what these two things are, which is a reasonable guess, right? We had those things on our screen here, but you have to read the postulate carefully. The postulate says it's the eigenvalues. And so the correct answer here is 1 and -1. Cool, okay. Let's go on to a second question. This one is, again, using another postulate. I'll read it out first. The result of a measurement of spin along the z-axis is -1. Okay, so I've taken my spin measuring tape and I measure along the z-axis, and what I get is a -1. Okay. What is the wave function of the electron immediately after the measurement? So the hint here is to think about the collapse postulate. So again, in quantum mechanics, as soon as I measure something, I apply my quantum measuring tape, it's going to change the thing I'm measuring. And so now we're saying, all right, I measured the value -1. You should be able to figure out what state the quantum object is now in. So again, I'll throw up a poll here so that you can submit your answer. And again, I will just mention these polls are designed to be tricky and confusing. So make sure to think about the postulate very carefully and give your answer in the poll. The attendance code is 6039. It's just in the bottom right of the slides here. Okay, so I'll just wait until about 50% of people have given their answers, and then I will try this problem myself. Okay, so looks like 50% of people have answered. I'll go ahead and solve this myself. Now, I'm going to cheat a little bit. I don't know if it's considered cheating, but I'm going to take my own advice and go back to this first slide and look at the collapse postulate, just to remember what that is. Again, I would highly recommend, if this slide works for you, literally have this slide open next to you as you're doing the homework. You don't have to memorize these, by the way. And I would not recommend trying to memorize the postulates. Just have a reference open next to you and use that. It's totally fine. Okay, so the collapse postulate. After a measurement, our quantum object is equal to the eigenvector corresponding to the observed eigenvalue. Okay, so this involves a lot of things. This involves both the eigenvector and the eigenvalue. But the key thing here is that it's saying our quantum state is going to be the eigenvector. It's equal to the eigenvector. So let's go back to our question. The result of a measurement of spin along the z-axis is -1. So this -1 is our eigenvalue. We're asked, what is the wave function equal to immediately after the measurement? Well, we know from the collapse postulate, it will be equal to the eigenvector associated with the eigenvalue. So I go up here, I find where that eigenvalue appears, and I know that my answer will be the associated eigenvector. So this thing, remember, is equal to ket1, and that's the correct answer. So I'm not going to give sort of more intuitive explanations for why the other answers are wrong. My #1 piece of advice is just follow these postulates letter by letter, and you'll always get the right answer. Okay, so we got one more problem coming up, but before we do that one, I'm just going to review one more piece of the Stern-Gerlach experiment. We had a whole bunch of diagrams like this when we were talking about it last week, right? Where we sent our electron through the magnets and it would hit one part of the screen. So as a refresher, where does the electron go in this case? We have an electron that is in a 50-50 superposition of spin up and spin down, or ket0 and ket1. Remember this 0.71 figure, it's just 1/√2, which might look a bit more familiar. Right, so we have an electron in a 50-50 superposition, ket0 and ket1, and you're sending it through the Z Stern-Gerlach magnet in the Z direction, right? And the question was, where does this electron deflect to? And the answer is that it deflects 50% of the time to 1 and 50% of the time to 3. And the justification for that was just that, there's a 50% chance that you will measure this electron in the ket0 state and a 50% chance that you measure it in the ket1 state. You took a screenshot of the slide. That's awesome. I will also post the slides, so don't worry about doing that. But yes, I would 100% recommend having a reference open. All of these postulates are for isolated quantum systems. Yes, so this is a technicality. Don't worry too much about it. But yeah, this assumes that the quantum system that you're considering is isolated, not affected by its environment, that kind of thing. May we see the poll result? Sure. So for that last question, these were the results. Okay. So let me move on to the actual problem we're going to ask here then. I just bring this up, this Stern-Gerlach example. Remember this, that the answer is the electron goes to 1 and 3. Okay, so let's do one more problem. What is the probability of the result of measuring the spin of the electron in state psi being 1? Follow-up question, what is the result of it being -1? Okay, and then we'll give you a hint here. Think about the probability postulate. the probability, and I've copied it here for you, the probability of observing an eigenvalue is the modulus square of the inner product of the corresponding eigenvector with psi. So again, I will throw up a poll for this. And again, my advice would be try and follow the postulates as closely as you can to get the correct answer. I'll wait until about 50% of people have answered, and then I will solve the question on my own. Okay, so a question over here. In Schrodinger's equation, for example, the energy operator is a function. Operators can be matrices and functions, right? And how do you convert between those? Yes, absolutely. So you might have noticed when we were talking about the guitar strings, we called them eigenfunctions, right? The different modes were called eigenfunctions. Whereas here we're talking about eigenvectors. Those two things are equivalent. And the sort of like a hand wavy way of saying how you would convert from one to the other is that, so imagine what the definition of a function is, right? A function is something where you plug in an input and you get an output. Now, if I had a function that has only, two possible inputs and two possible outputs, I could represent that as a vector with two entries, right? If I had a function that has, maybe it takes all numbers from 1 to 100, and it has different outcomes for all those numbers 1 to 100, I could represent that as a 100-dimensional vector that's just a list of all those different outcomes. Now, if you go to the extreme of this, what if I have a function that takes any number on the real number line? Then there's infinitely many outcomes, but there's nothing saying we can't have an infinite dimensional vector, right? And so what you would have is you would have a vector with infinitely many entries, one for each possible value you could plug into that function. So one way of thinking about a function is it's kind of just like an infinite dimensional vector. And that's kind of the connection between the function world and the vector world. Okay, so about 50% of people have answered here. I'll go ahead and solve it myself. And then we've only got one more slide after this. Okay, so again here, my advice, just follow the letters of the law very precisely, right? The question is, what's the probability of the result of measuring the spin of the electron in the state ket psi being +1, and what's the probability of -1? So here, we're calling out these two measurement values, which remember are eigenvalues, right? That comes from our measurement postulate. So now we go to the probability postulate, and we see that the probability of observing an eigenvalue, in other words, if I simplify the language here, measuring a quantity, right? That's all this is saying. The probability of measuring some quantity is the modulus square of the inner product of the corresponding eigenvector with psi. So here, the probability is just the modulus square of the inner product. We'll have an inner product, or sorry, modulus all squared. And then on the inside is the inner product of the corresponding eigenvector. So I'll just do it for +1 here. The corresponding eigenvector for +1 is ket 0 with ket psi. Okay, so you work this out. Our definition of ket psi is given up here. You work this out on your calculator, you should get 0.5. And if you do the same thing with ket 1, you should also get 0.5. So the answers there were half and half. Okay, so that brings us to the end of our examples. I'm just going to do some real quick key takeaways, and then we'll end off the required portion and go on to the optional content of the lab. So first key point was when a system that shows wave-like behavior is confined, the wave modes get quantized, right? So again, lots of new words in there, but this was the example with the guitar strings. When we fix two ends of the guitar strings, we always get these discrete modes, right? It always vibrates in a certain way. There's certain, you can imagine some weird and random shape of the string that we're just not going to see, right? Okay, and that's a result of waves being confined. At the scale of electrons, everything shows wave-like behavior. Therefore, everything shows quantization when it's confined. So we talked about several examples of what being confined means. That can be the Coulomb force holding you inside an atom. That can be an optical tweezer holding an atom in place. It could be dozens of other things. But yeah, anything at the quantum scale, when it's confined, exhibits this quantization of modes. And then finally, the postulates of quantum mechanics are the rules that quantum systems are observed to follow. So I am just going to spend like another minute or so explaining what this last point means. The postulates are often introduced as just kind of, we pull it out of thin air and say like, oh yeah, these are the postulates, take them for granted. I just want to illustrate a bit what they are. So over here on the left, we're going to have the real world. Right, and all I mean by the real world is these are physical things that you can see. So these are electrons. These are, bar magnets, right? And spins in electrons, and waves in a pool, and all that kind of thing, right? We have the real world over here. Now, we also have the mathematical world over here, right? And the mathematical world is nice because we can work things out without needing to do a physical experiment. We can just draw stuff on a piece of paper and it'll work out. So in the math world, we have matrices, right? We have our X, Y, and Z matrices. We have state vectors, right? We have something like ket psi. We have inner products and modulus squared and something like we just did, right? All of these different expressions in the math world. The way to think about the postulates is rules that link these two worlds, right? So the postulates are basically the thing that sits in the middle and links these two worlds. So if I want to go from, an electron in the real world, and I want to figure out how you write that in math, I use a postulate, the wave function postulate, right? If I have something in math, like an inner product, and I want to know what that looks like in the real world, I use a postulate. This would be the probability postulate, right? And so all of these postulates are just rules that we have come up with based on observing the real world, right? We look at what happens in experiments, and we've come up with these rules that accurately describe them in the world of math. Okay, so another further few readings. If you are interested in any of the stuff we talked about today, all of these are great resources for sure. And now I'll throw up the post-lab Zoom poll. I apologize for going a little bit over time. But yeah, does anybody have any questions that we can talk about now? Oh yeah, so I will say as well, we can go back to the postulate slide. Oops. To the postulate slide quickly, because I did say I wanted to go through this example first. And so we've gone through the example, but if you still have questions about any of the postulates, I am happy to talk about that now as well. Okay, so awesome, there's a Discord server. That's so cool, good job. Did I not do the last problem? I did do the last problem, perhaps a little bit quickly, but definitely, yeah, you can go back and watch the recording. And I applied the probability postulate, exactly. So after confining, how do we keep the ion electron from vibrating in modes higher than those we require? That is an excellent question, because it's one of the major challenges of actually making a quantum computer, right? And so how do we do it is, I guess the answer depends on what system you're talking about. Usually the answer is quite complicated, because this is one of those sort of, yeah, it is a very significant challenge, because as we'll talk about actually in the optional content, if you plucked a guitar string randomly, the chance that you're going to put it into only modes 1 or 2 is like 0, right? You're definitely going to introduce some other weird modes that you might not want. And the same is true for quantum systems. So, the slightest little perturbation, the slightest bit of temperature, the slightest bit of light that hits your system might start vibrating at one of these modes you don't want. And we have to work really hard to keep that out of our experiments, for sure. Yes, so somebody just answered this question. I'll say it just for the record. Are the eigenvalues always real? So think about this, I guess, before I read the answer. Think about it from a physical perspective, right? Our measurement postulate, or wait, which one was it again? Sorry, observation postulate, this one. right? The only possible results of measuring an observable are the eigenvalues. Could I ever take a tape measure and measure the length of my desk to be 2i centimeters long, or 2i meters long or something, right? Hopefully you realize the answer there is no, that you can't really have a physical quantity that is imaginary. And so the eigenvalues you will get in quantum mechanics are always going to be real. And the reason for that is because operators are what we call Hermitian. It's just a property in linear algebra that means literally the operator only has real eigenvalues. How do you come up with these operators? That's a good question. How do you come up with the operators? I guess I've always kind of just taken them for granted. I think perhaps the best answer to this, although I'm not exactly sure, perhaps the best answer is just based on observation again, right? So if you know that there's sort of, in the Stern-Gerlach experiment, you know that there's 3 different directions you can measure, you know that those directions are always going to give you sort of a +1 or a -1 measurement, you can use those properties to sort of reverse engineer what the matrix must have looked like to have those specific eigenvalues and these sort of 3 orthogonal directions. You would get a unique solution that is the X, Y, and Z matrices. In other cases, I'm not really sure though. I think it would just be based on observation. So somebody asks, are all Hermitian operators unitary and are all unitary operators Hermitian? This is something you can definitely just look up. It's one of those linear algebra facts. I don't want to give a wrong answer, so I'm not going to answer it right now. But what should the answer be? There's probably a nice, elegant explanation, but I'm not thinking of it right now. Christine, no. Okay, so somebody says no in the chat. Possibly that's true. Like one of them should subsume the other one. And all I mean by that is like all Hermitians should be unitaries, all unitaries should be Hermitian. I think it's, yeah, okay. I'm not going to answer because I don't want to give the wrong information. Okay, any other questions? Or shall we move on to the optional content? All right, someone says we should move on. Let's move on. Actually, wait, okay, there's a few more questions. Let me answer like a couple more questions before we go. Do these postulates stand for all interpretations of quantum mechanics? Yes. So the postulates are sort of like the ground rules that we've developed from observing various experiments. The interpretations of quantum mechanics are possible theories about why the postulates are the way they are. That's all. So yeah, the postulates are always the same, even for different interpretations. The access code for today's quiz is in the bottom right of the slide, 6039. But X, Y, and Z are arbitrary. How do we break the symmetry and say this operator is the one we need? I see. So the explanation I gave before this was just that if you have 3 orthogonal directions and you know what the eigenvalues of those matrices should be, I think I said that you get a unique solution. You don't get a unique solution. I believe there's still several degrees of freedom in it, but you can choose arbitrarily one of the matrices to be nice, right? So the Z matrix, we would just choose it to be a nice matrix like that. And then once you fix one of them, you can come up with what the other matrices must be. I'm not sure if that's exactly your question, but to break the symmetry, as you're saying, usually there is an arbitrary choice involved. There's some very deep reasons for this in linear algebra and representation theory, but the language of linear algebra is not perfectly suited to quantum mechanics. It works with some of these restrictions. So for example, only working with operators that are Hermitian, right? That is one example of a restriction. The basic language of matrices in linear algebra is not sufficient. Well, it's sufficient, but it's actually too much to describe what we observe in quantum mechanics. So oftentimes there will be these arbitrary degrees of freedom, and we make a choice that just makes our life easy. And that's how we get our standards and the norms that we use. Okay, cool. So I am going to move on to the optional content. Now, as I said, the optional content is going back to sort of the first half of the lab, which is talking about guitar strings, right? So let's try and forget all of the stuff about the postulates for now and go back to the example of guitar strings. Now, a quantum state is represented by its wave function psi. This is the wave function postulate, right? So what might that look like in the world of a guitar? So let's pluck a guitar string, right? And as I sort of alluded to before, when you pluck a guitar string in an arbitrary place with an arbitrary force, oops, turn off this pole. When you pluck a guitar string, there is like virtually zero chance that you're going to pluck it in the perfect way to create the first or second or third mode of vibration. So the question is then, I told you that the string can only vibrate in these specific ways. So if you pluck the string in a way that's not one of those specific modes, what happens? So here's just a picture sort of demonstrating what this looks like. You pluck the string, and maybe you end up with a shape that looks like this, right? So just to be clear here, it's not the first mode. It's not the second mode. Oops, that was a terrible drawing. It's not the second mode, right? It is something else, right? It's not one of the modes of vibration. So if you pull the string in this, in this shape, which you can physically force the string into that shape and you release it, what happens? Well, I'll tell you what does not happen. It doesn't turn into a new mode of vibration, right? The rule still holds that you'll only ever see the discrete modes we talked about. So what does happen is you end up with a superposition. Now, this is a mind-blowing fact of mathematics, which I'll try and explain a little bit. But if we look at our actual shape here, this shape is a superposition of all of the different modes we saw. Okay, so you can actually describe this shape by summing all of these together. Again, adding up the modes, summing them, linear combination, all of those are the same idea. Now, we have some cool slides here to sort of demonstrate how this works, right? So this is our string. This is the shape that we have plucked, right? And as I said before, this mode 1 does not fit that string, right? And so if we just had the first mode, that is clearly not a very good match, right? And so we can conclude, okay, our string's not in the first mode. We already knew that. I know it sounds obvious, but bear with me. What if we add the second mode? So all we're doing here, the modes are drawn separately on the right side of the screen, but then this blue line on the left side is just the sum of those two waves, right? So literally just at every point here, add them together and plot what the new value is. Just regular like summing of functions. Now this is, perhaps you can see it's starting to get a little bit better, right? Now we have this hump toward the left-hand side, which is kind of the pattern we see with the pluck, but it's still not perfect for sure. What if we add a third mode? Well, now the hump is moving, toward the correct location. If we do the first 5, this is starting to look pretty good, right? We have a hump in the correct location, but we still have some noise toward the sides here. If we go up to the first 8 modes, this is starting to look really good, right? We have our hump that is almost to the full height of what we want. We have a little bit of noise down here, but it's not as bad as it used to be. So we can keep going, right? Now we go up to the first 10, the noise gets a little bit better, so on and so on. Now this, again, what we're doing here is we're adding functions, which is linear combination of functions. I know that sounds weird, but a linear combination of functions, that is literally the definition of a superposition. And so this string that we plucked, by plucking it in something that was not one of those special modes, we don't randomly create a new mode because you can only have the specific modes we talked about. Instead, what we do is we create a superposition. And the superposition, if you add it all together, turns out to be the exact shape that we plucked. So on a string, we had this idea that summing these waves together can get you any shape that you want, right? If we pluck the string in any old way, we can always represent that plucked shape as a sum of these individual modes. The same thing is happening in qubits. When we talk about the superposition of two qubits, this is just like saying we're taking a sum of the first mode and the second mode. And we're getting some new novel type of wave that is not one of the individual modes. Again, we're not creating a new mode, right? We still only have these basic ones. Instead, we're creating a superposition. Now, the fundamental idea here is that the reason we do not create a new mode is because of the confinement and quantization stuff we talked about at the beginning. And so the only possible thing that could happen here is a superposition. Your string cannot exist on its own in this shape that you plucked. So instead, it has to be a superposition of the underlying modes. So just a technical term here, I guess, if you've heard of Fourier analysis, Fourier transforms, Fourier series, anything with the name Fourier in it is basically this idea of summing up different waves to get arbitrary shapes. Okay, so I'm going to pause here and just check. This is the same as the Fourier series. Yes. Yes. Yeah. So all of this is linked to Fourier transforms. Could you remind us why we only use two-level systems? Yeah. So that was, I forget exactly when I covered that, but the basic and like the simplest answer, I guess the primary answer, is that using more than two levels in a system is very hard to control, right? And actually, you can kind of think about it in terms of these strings as well. If you have this very complicated shape like our pluck, you need at least 10 modes to describe it, right? And handling all of those different modes and seeing what they sum to and trying to figure out what those modes are is extremely difficult, right? Whereas if we only ever have superpositions of the first two modes, it should, in theory, be a lot simpler to take, perhaps we have some shape that looks like this, right? It's a lot easier to decompose that into our two modes than if we were trying to consider like 10 or 20 different modes. So usually the answer to that, why we only use two systems, is either physical constraints or just to make our lives simpler. So when we pluck it, it's a composition of different modes. After some time, will it return to one of the modes or stay in the same irregular mode? We're going to get to that in a slide in the near future. The classical bit argument also works. Yeah, a lot of our theory that we've already developed is based on classical bits. Are electron orbitals pure modes, or can they be a superposition? Electron orbitals can be in superpositions, absolutely. Or actually, well, let me clarify here. When you talk about orbitals in like a chemistry class, for example, like the s orbital or the p orbital, those are modes, right? The shapes that you'll sometimes see drawn, those are exactly like me drawing these shapes on a string, right? Those are what the modes look like in their pure form. But you can have superpositions of them. So you could have an electron that has some other weird shape around the atom. And the way that we would describe that is that it's in a superposition of being in the s orbital and the p orbital, for example. So you can have superpositions of orbitals. Okay, so let's come back to some of our postulates then and see how this applies to the guitar string. First of all, the observation postulate. So it said the only possible results of measuring an observable are the eigenvalues of its operator. So again, when you're measuring something, step one is to figure out what your operator or matrix is. Step two is to figure out what the eigenvalues and eigenvectors of that operator are. On a guitar, we have the eigenfunctions, which again are these modes of vibration. If you try to see the string, so if you can literally try this yourself, look at a guitar string, you will only see one of the modes, right? So if you look at a string, usually you'll just see it vibrating. Well, actually, I shouldn't say that. You'll see only one of the modes vibrating, right? You won't actually see this really convoluted, weird pattern of vibration on the string. You will actually see one of the modes, right? It'll be vibrating in a clear pattern. Now, that does not mean that it's only in that mode, right? But that's what you will see. Your eye will automatically see one of the modes. We can also tie this to the probability postulate, right? So again, the probability postulate, just as a reminder, says that the probability of observing an eigenvalue is the modulus square of the inner product of the corresponding eigenvector with psi, which again is a lot of words just to describe this, right? On the guitar, when you look and see the string, the probability of seeing a particular mode depends on its contribution to the initial wave function. So again, if I did my initial pluck that looked something like this, maybe there's a lot of the first mode, there's a lot of the second mode, but maybe the third mode is really, really small, something like that, right? Then there would be a higher probability of me seeing the string vibrating in the first mode or the second mode, very low chance that I would observe it vibrating in the third mode. Okay, last one, the collapse postulate. So after your measurement, in this case, well, yeah, I'll just read the postulate first. After the measurement, psi is equal to the eigenvector corresponding to the observed eigenvalue. So I take out my quantum measuring tape, I measure a thing, I get that the value is +1, it changes the thing I measured. How does it change it? It changes it to the eigenvector corresponding with what I observed as the measurement. On a guitar, if you look at the string, you will not see it change between multiple modes, right? If you look at it, you'll see it remain just in one mode of vibration. This one is not as good of an analogy, but you can kind of think of it as the same idea. Like once you see a particular mode on the string, you're not going to see it change until you wait for an extended period of time where eventually the string will just die out and not really be vibrating much anymore at all. So again, the reason we talk about guitar strings is because one-dimensional is easier to visualize than three-dimensional for quantum systems, but the same ideas apply. It's all about these superpositions of confined modes of vibration, and that's why that's sort of why you'll hear people talk in terms in physics to say like, oh, the electron has a new vibration or it's increased its vibrational level. It's because you can picture it as literal vibrations on a string. So it sounds weird, but hopefully now it starts to make at least a bit of sense. Okay, so any questions, I guess, on anything I covered? This is the end of the optional content. It's just to kind of talk about the postulates in the context of guitar strings and to introduce the Fourier series and Fourier analysis, which is this idea. Any questions about any of this? Okay, so one person asks, will I see two different modes if I look at the guitar string two different times? So this is where I think the analogy breaks down a little bit, because like when you're looking at a guitar string and seeing only one mode, I mean, that's not really a characteristic of the superposition. That's just the way that your brain operates. It sees and interprets only one mode. So if you look back and if you look away and look back at the string, you might see a second mode. That's not how it works in quantum, right? In quantum mechanics, once you measure it, it stays in that eigenvector until you do something else to it. So different modes are different eigenstates, exactly. And so there was a slide earlier in the presentation, I won't go back to it, but here I wrote it, where, yeah, so the eigenstates, exactly as you said, the eigenstates here are ket 0 and ket 1. Those exactly correspond to the modes of vibration 1 and 2. The analogy of the string and particle in a box will be discussed later. I actually don't think it will, unfortunately. But I mean, you've already learned enough to fully understand that example. So usually, well, not usually, but one thing that you can be taught is the analogy between a guitar string, right? Which suppose that this is not exactly what it looks like on a guitar, but suppose we have a box and we put a guitar string in here and we can pluck it with either of the two, with any of the different modes of vibration, right? This you can kind of this can be the visual representation of a particle in a box. So if you somehow confine a particle inside a box, you know that particle's wave function will always be in one of these modes of vibration. So do you ever literally put a particle in a box? Not really. The box is a metaphor for the Coulomb force or for an optical tweezer or something like that. But it is the same idea. You can picture, roughly speaking, the Coulomb force holding an electron inside an orbital to be kind of like a box, right? Holding the electron in a particular area, and that causes the electron's wave function to have these specific modes. Just as soon as we measure it, when does it get back to its superposed state again? So it doesn't unless you do something to it, right? So for example, if I had a superposition, just to be a bit more concrete, if I had a superposition of 0 and 1, this, and suppose, so actually, let's use the Stern-Gerlach experiment. So suppose this is a superposition of up and down, right? I pass it through a Z measurement. And then let's say on the other side, we get it to be spin up, right? Remember, there's a 50-50 chance it'll be spin up or spin down. Let's say we measure it as +1, and so our state vector is now the eigenvector, which is ket up. That will stay out of a superposition. It'll stay as one of the basis states unless we do something else to it. So for example, here, we could apply a Hadamard gate to it, and we would get back to a superposition. But applying that Hadamard gate would have to be, some physical process that you as a human go and do to the system, if that makes sense. So to do what we would need Schrodinger equation, and we aren't doing that here. People would run away with the Schrodinger equation. So I mean, well, one of the postulates we talked about is already basically the Schrodinger equation, right? Yes, the Schrodinger equation looks scary, and it is scary in some cases, but it's also very straightforward in some cases. I think that I went over this in the previous lab. I don't remember if it was in this section, but if we drop all of the constants and stuff from the Schrodinger equation, there's actually a very clean way to think about it. It basically says this, right? Again, I've just dropped the constants. Now, you have to know some calculus for this. So if you don't know calculus, don't worry. You definitely don't need this for this course. But for those of you that do, this is a differential equation, right? And if I were to draw it in regular calculus notation that you're more used to, we might have d dt of f of x equals a times f of x, for example. And this a is just any constant. That's exactly what the Schrodinger equation is telling us. The only difference is that instead of a function, we now have vectors. And that kind of goes back to my hand-wavy explanation of how you link between vectors and functions. So all the Schrodinger equation is it's telling us when you differentiate a state vector, right? When you take its slope as a function of time, what do you get? Well, we're going to say that you get this thing called a Hamiltonian, which is just the Hamiltonian does not have to be constant, but in the simplest case, the Hamiltonian is constant times the state vector. Now, if you do know a little bit of calculus, you can solve this differential equation, and you will get that f of x is equal to some constant. I'm going to be sloppy with my constants here, but it's e to the power ax, right? And so you can work backwards from here to confirm that this is true. If you take the derivative of f, you'll get a times e to the ax, which is indeed what we had here. And so just like in regular calculus, we can do the same thing with a Hamiltonian, and we get that our state vector psi, which remember is the same thing as f, that's equal to e to the power of the constant h times x in this case, and x, well, oh wait, what did I do? d dt, sorry. Anyway, all these things should be functions of t, not x. It's my bad. T, and then up here we also have t. Right? And then, oh, sorry, I should also write, then you also have to have the original function here. So I am being sloppy with notation here, but the basic idea is that you can use the tools of calculus, which you already know, to solve this differential equation. It's an easy differential equation, and you get the Hamiltonian evolution equation. And so I believe somebody else put in the chat earlier that a unitary operator is equal to, well, again, I dropped constants, but roughly equal to something like this, which is exactly true. this is where it comes from. It comes from the Schrodinger equation. Now, totally, this is totally a rabbit hole. Don't worry if you don't understand this. I know that someone in the chat literally warned me not to do this because it'll scare people. The thing with the Schrodinger equation, though, is unless you're doing some very theoretical ground level physics, you almost never have to actually work with the Schrodinger equation, right? Like, so in my day-to-day job, for example, the only thing I ever need to know is this. It would be just as well if I had no idea how you get that, right? But you can just start with that equation and do everything I ever do in my research, and that's fine. So Schrodinger equation, it's the base, like it's the foundation of where these things come from, but usually we don't think about the foundation. Usually we think about things that are a little bit higher level that come from the Schrodinger equation. So don't worry about this, but if you are interested and you know calculus, that's a little bit of background. Okay, cool. Schrodinger equation, people run away. Hopefully they didn't. Why are there so many logic gates? Oh, why are there too many logic gates in quantum? Interesting. So I'm going to interpret this question as sort of asking, like, why are there more logic gates in quantum than there are in classical computing, like AND gates and OR gates and stuff? The basic answer there is just because a quantum state that is a vector of two numbers is more complicated and has more information inside of it than a single bit, right? And so therefore you can do more things with a state vector than you could do with just a bit. Okay, it's all great, but getting the chunks of knowledge to link stuff together is difficult. At what point can I say I truly understand the basics of quantum mechanics? I mean, it depends what your definition of the basics is, but I would say after these past 3 weeks, that's the basics of quantum mechanics. How I would personally define it is if you know the postulates and have some intuitive understanding for why the postulates exist, then you know the basics of quantum mechanics. Obviously, there's a bunch more you can do from there, but yeah. And I totally agree that there's sort of a lot of disconnected ideas here that it will take a while to pull together. So I apologize for that. I think we're trying to make these things seem cohesive as best we can, but a lot of times the best solution is just to spend some time with it, run through examples, try it yourself, and you do have all the tools you need to have a comprehensive picture at this point. Okay, and now we're talking about Tony Stark and Elon Musk. Okay, here's another question. As soon as my measured electron hits the screen, does it change into a superimposed state? I think if I'm interpreting it correctly, just the opposite. As soon as it hits the screen, it collapses to a non-superposition, right? So for example, in our experiment down here in the bottom right of the slide, if I started off with a superposition, the moment it hits the screen, it will collapse to either just spin up or spin down, right? And it'll no longer be in a superposition. You are measuring it with the magnet. Yes, but even when it goes through the magnet, it's still going to be in a superposition. It's not going to come out of that superposition until it hits the screen or it goes by a detector or something like that. So even going through a magnet, that's fine. It'll still stay in a superposition. It doesn't collapse until you measure it. And that's kind of the fundamental point here, is that measurement is what changes quantum states. Okay, so I think I will wrap things up there. Thank you to all of you who stayed out to the end. I hope this was at least somewhat entertaining. Good luck with the homework this week. Definitely try and post on Piazza if you run into any issues. But I hope that the poll questions we had toward the end of the required content, that's basically what all the homework is. It's all just applying the postulates. So remember my advice, have a reference open, read it word for word, and just be really careful, and you should be fine. So have a good week, everyone, and we will see you back next week to start talking more about quantum computing. Specifically, we'll see you then. Thank you.